remains constant, right? So that's a very important thing to remember in all cases when we are describing, um, a phase change. We have to talk about the temperature to say that it is constant, right? This graph here, from time to time, they might ask you questions related to graphs like these, and sometimes you have to give an annotated diagram or an explanation as to what is happening at the different segments, right? So as regards to this, let's just start from A to B, right? Clearly from A to B, what we're seeing happening there is an increase in temperature, right? Now that increase in temperature is really giving the particles enough kinetic energy, so much so that they can reach to a point where they reach the temperature that is required to basically change the state from solid to liquid. Where we see at BC, that is what is happening there. So at BC, as we rightfully said, that the temperature is going to remain constant because the heat that's supplied to the solid is used to overcome the force of attraction that holds the particles together. It says that the constant temperature is called the melting point. So one of the very important points here is to understand that, let's just imagine that you're melting some ice, right? When you're melting the ice, you're still applying heat to it. Now, what we're saying is that there is no increase in the kinetic energy. However, there is going to be heat required to essentially overcome the force of attraction. And if we're overcoming the force of attraction, what that means to us is that the particles are moving further apart from each other. So in essence, what is happening at that point from B to C is that there is an increase in potential energy, but there is no increase in the kinetic energy. All right? Let me know if you guys kind of follow what I'm saying so far.
Let's see.
So you have to remember that the heat that is now supplied during B and C is really used to stretch the particles further apart, which is to weaken the force of attraction, right? So much so that the particles can now reach to that state of um of liquid, right? So somewhere in your book you can make note of it to say that there is an increase in the potential energy, right? There's an increase in the potential energy at B to C. At B to C, there's an increase in the potential energy at B to C, and this is due to the fact that the particles are moving further apart from each other. So you can paraphrase that.
But there is an increase in potential energy.
Yes, there's an increase in potential energy, right? What else did I say just now? Why is that potential energy increasing there? Can somebody tell me why is the potential energy increasing? Hmm?
Because the force of attraction is getting weaker.
Force of attraction is getting weaker, yes. But what else can we say? When the force of attraction gets weaker, what does that tells us about the particles?
They're moving further from each other.
Say it again.
They're moving further away from each other?
They're moving further away from each other. If they're moving further away from each other, right, means that the distance is increasing, right, of separation. That now tells us that potential energy is going to increase. Remember, potential energy has to do with the height of something for the most part, right? So let's imagine that the particle, let me see if I can draw it on the screen here. Let's imagine that this is where the particles are located, right? And they are compact together. Now, imagine that the particle has now moved from here to here, right? It has moved from this ground level. So this is the ground level. That's the ground level, right? And it has now reached to this point. If it reach up there, so isn't it gaining potential energy now? Wouldn't we say that it's gaining potential energy?
Sir, can you repeat, please, sir?
So imagine that these are the particles, right? And when you reach A to B, the particles now are moving further apart from each other. So one example is that one particle could have been moving to this point. If the particle is here, right, wouldn't we agree that it would have more potential energy because it is moving from a ground level to a higher distance, so to speak?
Yes, sir.
Right? So you must remember this to say that there's an increase in potential energy because the distance of separation between the molecules is increasing. All right? So there's an increase in potential energy. Right? Due to the fact that there's an increase in separation of the particles. You can even write this to say at this point, there is no increase in the kinetic energy of the molecules. So you can write it, say that at this point, we're talking about from A to B now. I mean, not A to B, from B to C rather. So at this point, there is no increase in the kinetic energy. Hence, the temperature will remain constant. Hence, the temperature will remain constant. Anybody know why the temperature will remain constant?
So is it because it's changing state?
All right, it is changed. Yes, we know that, but I want a little bit more. We know it's changing state. The temperature remains constant, but what else can we say about temperature? You know, like what would make it, remain constant? You know, what I said it earlier, but I just want to see if you guys are following and understand what we mean. By the way, what is temperature? Like, what is temperature? How do you talk about temperature of something? Or yeah, well, how do you describe that? Come on, guys. How do you describe the temperature of something? How do you go about describing the temperature of something?
Sir, the average kinetic energy in a particle.
Exactly. Exactly. Remember, we give you that information already now. I don't know why you guys getting information and you're not making use of it. The temperature is the average kinetic energy. I would just, what did we say about the kinetic energy when the temperature is constant? Come on, guys. What did we say about the kinetic energy when the temperature is constant? You guys joking out this thing in the man.
Sir, does it remain the same?
It remains the same. So if the kinetic energy is the same or remains constant, then that just simply shows us that there will not be an increase in temperature. From the mere fact we know that the kinetic energy is constant, right? Then we don't expect that our temperature is going to increase. So if anytime we talk about constant temperature, in the back of your mind, you must know that the kinetic energy of the molecules are constant, meaning that they're not increasing their speed at any point in time. They are just at an average kinetic energy or average. They just have an average kinetic energy, or they're moving at a set speed for the most part. All right. Now, when we consider from C to D, right? From C to D, we see that there's an increase in temperature, right? At this point here, this is that point when the molecules in the liquid is now gaining more kinetic energy, so much so that they can reach to the point, right, when they can now transition from a liquid into a gas for the most part, right? So from C to D, that is when you would have that process, you're gearing up for the process of boiling to take place. So exactly at D, that is when boiling would take place. That's what I mean? But as soon as we reach at D to E, right, you can now see that the temperature at that point is also going to be remaining constant, right? And with that, it says here that this is because the energy absorbed is used to overcome the intermolecular forces between the particles of the liquid rather than increasing the temperature. So here we're now seeing what is happening in this phase. So from D to E, the reason why our temperature is constant is because the heat that is supplied to the system is now being used to essentially overcome the intermolecular forces, which is the same thing as the attractive forces for the most part. Because what you have to understand, ladies and gentlemen, when we consider molecules, right, or water on a whole, they are molecules. And for us now to break them apart, we need a substantial amount of heat to break them apart from each other. So during that process from D to E, that is when you are essentially breaking those molecules apart, as something says, intermolecular forces. So there are intermolecular forces between the molecules in the water, right, that makes up the water, H2O, and you're now breaking that so much so that you can go into the process of steaming, or pretty much converting from a liquid to a gas. Now, what you must understand is that this is where the boiling starts to take place. Boiling would end at this point. Now, as boiling ends, right, you now have a scenario where you have completely gas being formed, because you would have now converted all of the liquid into gas. And once you do that, that gas is now able to increase in temperature and continue all the way up forever to and forever, right? So that's just pretty much what this graph is describing to us here. So we ought to be able to can annotate, describe what is happening from one era to one era. You must be able to can explain when boiling is taking place from this graph, when there's a change of phase, right? When the liquid is being heated up so that it reaches to boiling, all of that kind of niceness. You have to be able to can reproduce, right, this type of information here. And as it relates to the specific things that are happening, right, you must also note all of those things, especially when you talk about overcome the force of attraction, those things. Talk about overcome the intermolecular forces. That makes you sound like a physics student when you state those things. You understand me? And we expect that that is the information we want from you guys. We don't want any skimpy, thing. You understand? We want good quality information to show that you understand what was going on here. I wonder if we understand what's going on. Huh?
Yes, sir.
Yes, sir.
I don't want to fall asleep in my class, Let me see what's going over here, so. Right. Avia, you're following Avia Barnes? Barnes, respond to me and let me know if you're following for me, please. Oh, respect, Benny, respect, much respect. Lawrence, you see, me hearing from Avia now, You understand? So it's clear that she probably now focusing on the class. You see what I say? You know focusing on Ryan because me not call her name all now, You understand what I say? What you say yes sir for? Me not understand. What you saying yes sir about? Lawrence, let me know if you're following what Mr. Douglas said a while ago. Start write down names and call people parents, yeah man, cause me nah can't waste my time, I don't want to no waste phone parents time. Me I'll write down names and see what I going on. So Avia Barnes, me not hear them from she. So what I going on. McDonald, you good brethren, you understand what I going on, so?
Yes, sir.
I have so many students who are absent today, right? And I need to know why these students are absent. Matthew Plummer. Let me just go back to my register very quickly because I don't know skimpy thing, Let me try to show him, They will have a much lower melting point when compared to something else. So as we know already that melting would pretty much involve a process when the solid changes into the liquid state at a certain temperature, which is called a melting point, and also at a certain pressure when it is heated. Are we good with that information? Yes?
So, sir, if to draw like a graph, what temperature would we put as the general melting point?
No, if it's not stated to you as it relates to the substance and so forth, then you don't need to state the temperature, right? What you would just need to do is to just replicate the graph, right? And you know that melting would occur here, right? So melting would be essentially taking place here. So you just need to have temperature on this side of the graph, unless it is stated to you, right? Unless it is stated to you. But if we're dealing with water, we know that water melts at, let's take for example, 0 degrees Celsius. Chances are um, this temperature might be in kelvins. I don't know. Maybe it can be in kelvins. If it is in kelvins, then it means that at 273, that would be the temperature on the Kelvin scale that you would record right here, right? And we got that information from the fact that T is equal to my temperature in degrees plus 273.115 essentially. So at that particular temperature in terms of Kelvin, you would have melting taking place. All right. So once you don't have that information, then you don't need to kill yourself over that. Eventually, I'm going to show you how we can use these graphs to understand certain information, because what you're going to realize is that from time to time, we will need to find out the energy that was required to take or to heat up the solid so that it melts. And for that, now you're going to use these graphs to read the temperature difference and so forth. But we'll talk about that in some other lessons when we reach to that stage, right? How we're going to use this graph for our own benefit. Now, moving along, freezing, of course, is that process where a liquid changes into a solid at a certain temperature, which is what we call the freezing point, and pressure, which are pressure when it is cooled, basically. So there's a certain pressure that is required for when freezing is taking place, and in most cases, that's what we call the standard pressure for the most part, standard atmospheric pressure. Because what you have to understand, ladies and gentlemen, that there are several things that can affect these processes in nature. And one of the main things is what we call the atmospheric pressure. Can somebody go on the internet and research what is the standard atmospheric pressure for me, please? And just send it in the chat so we can document that information. So you can just go ahead and send it in the chat. I think it's what, 10,000 pascals, 10,000 kilopascals, or something of that nature. What is what? All right, somebody sent it here. Somebody said it is this. Let me send it here. Yeah. So it is you guys have to be sure about the answer. You know? I see some person sending several answers. I don't know whether I'm to accept your answers, yes or no, right? Some persons is saying 101.325 kilo pascals. By the way, whenever you are writing the unit for pascals, it's a capital P and a common A. If you write common P and common A, we're gonna mark you wrong. You understand? Just be mindful of that. Now, sir, you're having some Wi-Fi issues. That's why you're late. All right, now your mother, I'll call you. Can stay there. All right, I'll call your mother later on.
Sir, me?
Of course, you.
Sir, and tell her what?
What?
Sir, why you gonna call my mom?
Yeah, because you make the internet not working. You understand? When you have in my class, and every time you make it happen. Anyways,
Sir, what are you talking about?
I have less than a minute, so I'll restart my session here. Is that process through which, you know, oh, let me say something. Oh, sorry about that. Yeah, vaporization right, is that process, whereby atoms of or molecules in a liquid state gain sufficient energy to enter the gaseous state. All right. I'm trying to understand what you said, Win. Right. But when we're talking about the atmospheric pressure, I guess you're talking about that. So there are two ways we can write it. As we said, 101,325 pascals. So that's 101,325 pascals. Or you could write it as 101.325 kilopascals. Yeah. Right. Okay, great.
So vaporization is something close to evaporation.
Could you say it again?
Vaporization is the same thing as evaporation.
All right, so that's a very important question, bro. Very, very important question. We want to, let me see how much time we have left. I think we have enough time. Now, vaporization is linked to evaporation, right? But what you have to also understand that boiling is also linked to vaporization. They happen, two things can cause vaporization. Evaporation and boiling can cause vaporization. Further down in the lesson, we're going to look at what is boiling and what is vaporization. But you're indeed correct, but it's not the only process of vaporization. You follow me?
Yes, sir.
Yeah, man. So this is just what vaporization is defined as, right? Now let's continue. Can I? May I?
Yes, sir.
Yes, sir.
Another process that you guys will hear us talking about, is condensation, right? Condensation, of course, is when you now take back that gas and you bring it into the liquid form. Nothing new. You have heard about condensation before. We're not talking about condensed milk now, right? But condensation is what we're talking about, where you just pull the gas, right? And this happens every day in our lives. When you are cooking and so forth, and you find that water on the surface of the pot cover, right? That is as a result of vaporization. So what would generally happen is that the steam would come up, hit the pot cover, it's going to cool rapidly, and when it cools, it just convert back into liquid. You know what I mean? If you're adventurous enough, you can taste that water, and you're going to find that it's going to be very, very fresh, right? That is basically pure water. It's removing all of the, it's only water that is going to be vaporized mainly, right? So when you go at sea and you're lost and all of that, or you want water, you can boil seawater and collect the condensation, right, or the condensed water, which is basically collecting the steam and essentially allowing it to condense back into liquid form so that you can get fresh water to drink. It's going to be very fresh, of course. Anyways, that is that. What do you mean boil it in what? If it's there sea, well, as in maybe you live out on one of those islands, like a goat island or so, and probably some of you would, so or maybe you walk up on an island still. Maybe you buck up on an island and you can probably start boil some water, right? Yeah, that not gonna work. You know that not gonna work. But you could use the sun though. Like the sun will evaporate the water, So you could collect.
Sir, I'm asking, what would you put it in?
Oh, Zine, that me know that you ask, but let's just imagine that you live at Goat Island. You have your pot out there just to make life a little bit much easier. So you have Goat Island, so you have a pot. You just boil.
Sir, but you said lost at sea.
Yeah. You're right. So now we kind of correct myself, right? So yeah. Not being lost at sea. We know that probably not gonna work. But if you have one cheese pan at sea, then maybe you can light some fire on the boat. I don't know how skill it would be not to burn up the boat, right? But either way, you kind of get what I'm saying here, right? That's also a survival technique. Sublimation, right? That is a process where a solid goes straight into a vapor form without becoming a liquid. So that's something that happens when we are considering our curve, right? Whenever we're talking about state of matter, we know that that is a process that can happen, and it does. The solid does not go into liquid form, right? Does not go into liquid form in that process. So that's something you must remember as it relates to that. A typical diagram that you could draw to summarize all of these things is having a more like of a triangulated kind of diagram. So you have your gas right here, you have your solid, and then you have your liquid on this side, and you just use some arrows to show the process. So we know that going from liquid to gas, that's going to be called vaporization. From gas to liquid, we call that condensation. Right? We know from a solid to a liquid, that's going to be melting. From liquid to solid, that's going to be freezing. Right? Then now from solid straight to a gas, that is sublimation. There's another process here. I think they can refer to this as condensation, but I don't think that's the right term.
Sir, deposition.
Deposition. You're right. You're right. Thank you very much. Right.
Wait,
Then
sir, what is the position?
it's coming from a gas to a solid. But in some cases we can call it condensation, but it's the right terminology is deposition. Right? Deposition, deposition. Yeah. So that completes that. Once you have that down, then we kind of just show you what happens from the different standpoints here. Chemistry students would have known some of this information, right? So once we have that now, we soon reach to this. What we're doing here is just talking about theory for the most part. We soon reach to a point where we start doing certain calculations and so forth, right? But I just wanted to kind of get the framework and the basic stuff into play. Then we start considering calculations and so on, right? Once you are through with that, you can just let me know so I can move on to greater things. No, I think we are doing well for the most part. Um, it's it's now May. I think the end of June would be the last teaching month, right? And then now, when do you guys get exams for summer?
Sir, around June or like early July, somewhere there.
Sir, June, early July, yeah.
It's June. Yeah, it's in June. Okay. So we have to make use of this month of May to be able to kind of accomplish all of section B, right? Because we want to reserve, quite frankly, section C for starting the next school term that is in September. It would be good if we could reach over to section C in this month before we go off, because it will put us at an edge. But I think we can either way. I don't think it makes sense we try to rush it over that side, right? So section C can be a whole lot. But all right, I think you guys are. Mm, yeah. So fifth form. So if you guys, if you guys don't pay attention, if you don't pay attention, like time is flying so fast that if you buck your toe, you drop right on your face. You know what I mean? So I want you guys to, there was something I wanted you to show you guys. I saw it on Facebook.